Hello again. I hope you enjoyed yesterday's video and found it really useful. Back again today to do day 2 of the White Rose Maths problems of the day. We'll just mention that in case you didn't see yesterday, all of the links for where these problems of the day have come from or the app I'm using to record this are going to be in the description down below on the YouTube videos. So if you can't find the original email or you're not from my maths class but want to have a go at these questions, you can find links to the work below. White Rose Maths is fantastic. They are doing some online lessons on there as well. Can't praise them enough. I did not come up with these questions. I'm just helping you to answer them. So without further ado then, let's get on with day 2. So we're just going to have a look at the orange and the blue day 2 problems of the day. So here we go. Oh, and I do apologise that yesterday was covering some of the questions. I'm not sure how to stop that because my box on my screen, I'm moving to the other side, but on the recording it doesn't move. So I might just make myself smaller again so you can look at the question and then I'll make myself bigger to go through the answers. Okay, so day 1, we have got Ron, who has these digit cards. Remembering a digit just means a number. So 1, 4, and 6. He uses 2 of the cards to make a 2-digit number. How many even 2-digit numbers can he make? Well, there's a really important word in there, isn't there? Even. What do we know about even numbers? That's right, even numbers are things that can be split into 2 without a remainder, so equally split into 2. So all even numbers are going to end in 0, 2, 4, 6, and 8. Just think about your 2 times table. We can stop there because if I were to write the number 10, we can see it would end in a 0 like we've already written. Okay, so the first job is to look at those 3-digit cards and say, well, which are even numbers? 1 is not an even number. 4 and 6 are even numbers. So now we have to think about the combinations of these numbers, what we can do to make a 2-digit number that is even. Remember what I said about those even numbers, so in this case 4 and 6, have to be on the end or in the units column of our number. So I'm going to start off and I'm going to say, well, I want the 4 in my units column. So tens, units, I'm going to put the 4 in my units column. If I put the 4 in my units column, I have got 2 different options to put in my tens column to make a 2-digit number. So I'm going to put the 1 in there, and then I'm going to do it again with the 6. So straight away, I have created myself the numbers 14 and 64, and both are even because they have a 4 on the end. Okay, I think there might be some more though, because I haven't used my 6 on the end yet. So I'm now going to try again, and this time I'm going to put my 6 in the units column. Now this time, again, I have 2 options. I could use the 1 or the 4 in the tens. So I'm going to start with the 1, and then I'm going to do it again with the 4. So now I have created the numbers 16 and 46. I think that might be it, because if I try again and I have the 1 in the units column, we already know that the 1 is not an even number. So we end up with 14, 16, 46 and 64 being the 4 even numbers, or 4 2-digit even numbers we can make. Okay, question 2. 1/3 of the shape is shaded, true or false? Oh, this sounds like a nice question. Are they right or are they wrong? But you know my favourite thing in our maths lessons is we don't just answer our questions. I often then say back to you, well, prove it to me or give me a reason. So if you're going to choose true or false, you need to be able to explain why. Let's draw this shape out on our whiteboard. And I've got to make sure I copy it exactly. So we're going to have a look. We've got 3 rows and we've got 4 columns. And we've got some colouring in. 1, 2, 3, 4. So there is my copied rectangle. Well, let's think about what we know about 1/3. That is a fraction. And we would write that as 1/3. This is actually what we call a unit fraction because we have a 1 in the numerator. So our denominator is a 3. 1/3 means we need to split our shape into 3 equal groups. That's the key bit in fractions, isn't it? That each of those groups are equal. Well, let me use some other colours so we can see. If I colour in the bits that are left, do I end up with all 3 of my colours having the same amount? So I have got 1, 2, 3, 4 green squares, 1, 2, 3, 4 red squares, and 1, 2, 3, 4 blue squares. So 4, 4, 4. I have got 3 groups that are all equal. So it is true that 1/3 of the shape was shaded. Okay, let me just make myself a bit smaller again so you can have a look at this question. But as I say, the links are in the description below, or you can have a look at the original email I sent you, and then we'll have a go at this. Okay, so here we are having to tick all the calculations that are greater than 40. So there's another bit added to the bottom. It says, did you tick any without working them out? Is there any way you can tell me you know an answer is going to be greater than 40 without actually doing the calculation? Well, first of all, let's check that we remember what greater than means. So greater is equal to bigger or to more. So greater than means bigger than 40. Okay, let's have a look at the first calculation they've given us. 43 plus 39. Now, I think I know whether I can tick this one or not without even doing my addition. Because 43 is bigger than 40. We have our 4 tens. We've also then got 3 units. So this is already bigger than 40. And if I am adding a positive number, we know that adding means getting bigger. So we're already bigger. We're going to add on some more. We're going to get even bigger. So I'm going to tick this one as greater than 40 without even working it out. Okay, so 43 plus 39 is greater than 40. What about a 35 take away or minus 6? Well, 35 is smaller than 40 because we only have 3 tens, not 4 tens. So we're already smaller than 40, and then we're going to take away. When we take away, we get smaller. So we're already smaller, we're going to take away and get even smaller. So without working this one out, I know this one is not greater than 40. So I'm not going to give this one a green tick. We're going to have a look at the next one now. 23 plus 28. Okay, this one might seem a bit trickier to do at first, and you might actually want to work this one out. We should probably practice some of our column addition. So let's work this one out together on the whiteboard. Make sure when doing column addition, you are lining up your place value properly. So the 23 and the 28, you've got your units, 3 and 8, and your tens, 2 and 2, lined up correctly. Now with our column addition, we start with our units column. So 3 plus 8 is 11. So we're going to put a 1 in the units column and bring 1 over to underneath the tens column. Now we have 2 plus 2 plus 1, giving us 5. So 23 plus 28 is 51, which means this one needs a green tick. This one is greater than 40. Could we have worked that out without actually using our column addition? Let's think about our part wholes and what we know about the number 40. Well, I know that the number 4 could have 2 as a part, making 4 as the whole. Let's do a reminder for people of what a part-whole model looks like. So I have 4 as my whole at the top, 2 is a part, and 2 is another part. Well, what about if we times all of these by 10 to use our 40? So I'm just going to move them up the place value by putting a 0 in the units column. So now 40 is the whole, 20 is a part, and 20 is a part. If we go back to our 23 plus 28, both of these numbers are bigger than 20. So both of our parts are bigger. Our whole will also be bigger or greater than. So this one can have a tick as being greater than 40. Okay, just 2 calculations left to look at there. So the next one we've got is 10 times 7. Now I know you guys love your 10 times tables. You're all very good at it. Let's have a think about whether we're going to tick or not tick this one. Let's work it out using our times tables, counting in tens. In fact, I'm even going to use my fingers this time because I want you to make sure you're being accurate. So 1 times 10 is 10, 2 times 10 is 20, 3 times 10 is 30, 4 times 10 is 40, 5 times 10 is 50, 6 times 10 is 60, and 7 times 10 is 70. I've gone way past 40. 40 was all the way back here. I'm on 70. So this one definitely needs a tick because it is greater than 40. And we can remember that when we are timesing by 10, we are moving along the place value. So we would be putting a 0 in the units column on the 7 and making it into 70. So we could see that that one was going to be greater than. The last calculation we have got is 24 divided by 2. Now I know division is something that we still use a lot of visuals to help us practice, and that's fantastic. We also want to remember about our fact families, that we know some of our 2 times table, which means we also know our division facts. Think about what dividing actually means. You know I like the word share. When we are dividing out, we are sharing it out. In this case, we are dividing 24 and we are sharing it between 2 people. The 24 is already less than 40. And then I'm going to take that 24, I'm going to share it into 2 groups, meaning I'm breaking the 24 into smaller parts. So this one is definitely not going to be greater than 40. So it should be that out of our 5 calculations, 43 plus 39, 23 plus 28, and 10 times 7 have a tick, but 35 take away 6, and 24 divided by 2 do not have a tick. Well done. And that is day 2 orange questions completed. Do you stick around and have a go at the blue ones as well? So I'm just going to move on to day 2 blue here. Okay. So we've got very similar question again, but just a little bit trickier. This time, Ron's been joined by Eva, and each of them make a 3-digit number using these digit cards, 3, 6, and 8. Ron makes the largest even number possible, and Eva makes the smallest odd number possible. What is the difference between their numbers? So this is a case where we have to think about what do we know, what do we need to know, what can we work out, what calculations are required. Because there's not just going to be one step to the answer this time. I know we all like a nice quick answer, but sometimes we have to do lots of steps. So the first thing I think we should do is try and figure out Ron's number. It says it's the largest even number possible. So this is back to what we did on the orange page of what is an even number. Well, it's something that ends in 0, 2, 4, 6, and 8. So we have got 2 even numbers here. So I'll use the same color coding I did before. So 3 is not an even number, 6 is, and 8 is. So we know that Ron's even number has to end in either a 6 or an 8 in the units column. Does that mean we can put the other numbers in any order? Well, Let's have a think. This time it's a 3-digit number. So we need hundreds, tens, and units. So we've got our hundreds, our tens, and our units. So I'm going to choose the 8 in the units column as an even number. And then I'm going to choose to put the 6 in the hundreds and the 3 in the tens. And I've created the number 638, which is definitely even. But is it the largest even number we could get? I'm hoping some of you have noticed, by me just guessing, I've made a mistake here. This isn't as big as I could get. What we need to do to make the largest even number is have our largest possible number in the hundreds column, as long as it leaves us another even number. And as we have 2, it does. Our biggest number here is an 8. So I need my 8 in the hundreds column. So I'm going to rub out my first attempt and try a new number. I'm going to put an 8 in the hundreds column because it's our biggest number. Now I have to put the 6 in the units because it has to be an even number, and the 6 is my only even number left, which leaves me with the 3, which must have to go in the middle. So before I had 638, now I've got 836. That's much bigger. So Ron's number is 836. Now we've got to move on to ever. It says that ever makes the smallest odd number possible. Now, we haven't mentioned odd yet, but I'm hoping you've remembered that odd is the opposite to our even. So our even numbers end in 0, 2, 4, 6, 8. Our odd numbers end in 1, 3, 5, 7, 9. And that's the 3 in our digits. Our 3 is our odd number. So the odd number must be in the units column. And as we only have 1, it's got to be the 3. So I'm going to put the 3 in my units column to make sure it's an odd number. Now, ever needs to make the smallest one possible. So this time, out of my 2 remaining digits, the smaller one needs to go in the hundreds column. In this case, it's the 6. So we're going to have 683. Okay. So I have now figured out Ron's number, and I figured out Ever's number. But it's not the end of the question yet, is it? Because it actually asks us, what is the difference between their numbers? Now, you might remember me saying from yesterday or from our lessons that difference is one of those big clue words as to what calculation is required. Well, we are looking for the gap between 683 and 836. The gap is the difference or a missing number. So we are going to do a takeaway. Let me just show you that using a bar model to prove why we're doing that. So we have 836 as Ron's number. Part of it is 683, Ever's number, and the gap is this bit here. So we have our whole 836, our part 683, and we're looking for our difference, a takeaway. So this gives us a chance to practice some column subtraction. So let's have a go, making sure with our subtraction, our larger number is going on the top. 836, take away 683. And again, we know that we start with the units column. So 6 take away 3 is 3. 3 take away 8. We've got a problem here because 3 is too small to take 8 away from. So I need to come up the place value to the 8 and borrow 1 or regroup. So I'm going to pinch from that hundreds column, turning it into a 7. I'm going to move the 1 I pinched over. So now instead of having 3 tens, I have 13 tens. I can try again now to do 13 take away 8, which I know is 5. And it leaves me with 7 take away 6, which is 1. So the difference in Ron and Evan's numbers is 153. Okay, well done. There were lots of steps in that to figure out both numbers and then do a takeaway or a subtraction. So just make myself smaller again so you can read this question over here. But as I say, do have a look at the link below. Okay, so this time we are looking at fractions. We're looking at fractions that are greater than 1. So lucky old me, I'm going to start talking about pizza again. And I am filming this just before lunch, so it is making me quite hungry. Okay, we have to circle all the fractions that are greater than 1, but less than 2. So meaning bigger than 1, less than 2. Let's have a think about how we could write this down. So question mark is what we're looking for, and it is going to be greater than the number 1, but less than the number 2. This is just a chance for us to revise our greater than and less than signs. Remember, hungry crocodile is often how we've learnt it. It eats the bigger number, or the small pointy end points to the smaller number. So 1 will be smaller than our fraction, but our fraction will be smaller than 2. Okay, let's have a think about this then. What have we got here? We have got 12 fifths, 12 sixths, 12 sevenths, and 12 eighths. Okay, let's think about this pizza then. I'm going to draw out one pizza here. And looking at the first fraction, the 12 fifths, we know our denominator, the number 5, is how many slices we've cut it into. So I'm going to cut my pizza into 5 slices. 1, 2, 3, 4, 5. Now, we know these slices will all be the same size, but my drawing skills aren't very good. Now, the number on the top, the numerator, 12, is how many pieces or slices we've actually got. So my one pizza with 5 slices just isn't enough. I'm going to draw another pizza. And I'm going to cut this one into 5 slices too. 1, 2, 3, 4, 5. I'm going to count how many slices I've got all together. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 12. I've still not got enough. So I'm going to draw another pizza. Starting to get a bit greedy now, I think. 1, 2, 3, 4, 5. So if I count on from 10, 11, 12, 13, 14, 15, I've got enough slices now. So I'm going to colour in the 12 slices that I've eaten. But don't worry, I'm not on my own. I've shared them with my brother, my mum, and my dad. Okay. Here we go. We have got 3 pizzas. 2 of them have been eaten completely, and 1 of them has had 2 out of 5 slices. So let's think about how we could write that. We're going to go back to using our equivalent fractions here, and we're going to turn 12 fifths, which is called an improper fraction, because the numerator is bigger than the denominator. We're going to turn it into a mixed number where we use units and fractions. So I have got 2 whole pizzas, 2 wholes or 2 units. Then I have 2 out of 5 slices eaten on the 3rd. So 12 fifths is the same as 2 and 2 fifths. So is this number greater than 1? Well, yes, because I've got more than 1 whole pizza. Is it less than 2? No, because I've got more than 2 whole pizzas. So 12 fifths does not count. Let's have a go at the next one. I want us to see if we can do it without the drawing this time. So this time we have 12 sixths. Well, we need to think about, this is an improper fraction again. The 12 is bigger than the 6. How could we decide whether this is bigger than 1 and smaller than 2? Well, I would like to turn it into a mixed number. So we have to remember that 1 whole, like in my pizza example from the last fraction, is if we have all of the slices eaten. So if each pizza is cut into 6 slices, 6 of those slices are eaten, we have eaten a whole pizza. So 6 sixths equals 1. So then we need to use our 6 times table to see how many wholes. And actually, if I do how many 6s I can fit into 12, I know my times tables and I know that I can fit 2 6s completely into 12. So this equals 2 whole pizzas. No extra slices, we've just eaten 2 pizzas. So is this greater than 1? Yes. Is it less than 2? No, this is equal to 2. So 12 fifths doesn't work and 12 sixths doesn't work. Let's have a go at 12 sevenths. Okay, same again. We're going to convert it to a mixed number. So let's see how many whole pizzas we could make. Well, 7 slices, I eat 7 of them, 7 sevenths, definitely get 1. How many sevenths can I fit in? How many 7s can I fit into 12? Oh, well, 2 times 7 is 14, so I can't fit another whole one. So I can fit 1 whole pizza. And then what is left, or what is the difference between 7 and 12? I'm going to do my subtraction, or I'm going to count on to find that that is 5. So 12 sevenths is the same as 1 whole and 5 sevenths. Is this bigger than 1? Yes, we've got a whole and 5 sevenths. Is it less than 2? Yes, we have not reached 2 wholes. So 12 sevenths counts. Brilliant. We're going to use 12 sevenths and circle that one. And the last fraction, you may have seen where this is going now. Let's try 12 eighths. And let's turn this into a mixed number. So how many full eighths or full pizzas can I fit inside of 12? Can fit 1 full pizza of 8 slices. And then what's the difference? How many extra slices from 8 to 12? It is 4. So I have 1 and 4 eighths. Now you know what I'm like. I'm going to be mean and say, oh, we could change this fraction using our simplifying. What could we look at our 4 eighths? What common factor do we have to simplify? That's right, 4 goes into 4 and 8. So we're going to divide 4 by 4, which is 1, and we're going to divide 8 by 4, which is 2. So 4 eighths is the same as a half. So this fraction equals 1.5. Is 1.5 bigger than 1? Yep. Smaller than 2? Yep. So we could also circle 12 eighths. Okay, last question. You're doing really well at focusing. It's long videos, these ones. So the last question says, what fraction of this shape is shaded? Okay, so we have got a square here that's been cut up into more squares. So I'm going to draw this out onto my board. Make sure I'm copying it properly. We have 4 rows and 4 columns. So 1, 2, 3, 4. 1, 2, 3, 4. But the section that has been shaded, well, there's no complete squares coloured in, so I'm going to have to be quite careful with my colouring here. I'm going to colour in that, and I'm going to colour in that and that. You can see the concentration on my face to make sure I do this properly. Okay, now the way I've coloured it in might also give you a bit of a clue. But there we go, there is my representation of the diagram. And it asks us what fraction is shaded. Well, we know when we've done our fractions before, and actually from yesterday, that our denominator is the total options, and our numerator is what we want. Okay, so in this case, our numerator is going to be the coloured bits, Our total options is all of the bits. Okay, so green over all. Green over all. Well, that sounds nice and easy, doesn't it? Except the green isn't colouring a whole square. So if I count that as 1, I can't also count that as 1 because we know in fractions things must be equal. So here's what I'm going to do. I'm going to make everything match by turning all my other squares into the same as these. And you can see that these shapes, actually, we've coloured in a triangle or we've coloured in half of a square. So what I'm going to do now is I'm going to make sure that all of my squares have got that diagonal line splitting it into triangles. Okay. So now it looks like this. So now I can use this and I can just count the green triangles. There are 1, 2, 3, 4, 5, 6, 7. So the top or the numerator will be 7. And then I have to count all my triangles. So remembering not just the white ones, but all the triangles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Whew, I'm nearly out of breath. That was a lot of counting. Do you think there's an easier way that I could have done that? Let's have a think. Oh, well, it was in squares, wasn't it? And we know that we can use our array to do our columns by rows. 4 times 4 is 16. And then I'd cut each one of those in half. So it was now 2 triangles. I could have done 16 times 2 to get my 32. So the fraction of this shape that is shaded is 7/32 or 30 seconds. Could this be simplified? This cannot be simplified because 7 is a prime number, which means its only factors are 1 and itself. And 7 does not fit into 32. 32 is not a multiple of 7. So 7/32 is as small as this fraction can get. Well done. That was a really tricky question at the end there, thinking about how we make all of those shapes equal sizes. I hope you're enjoying these videos. I'm really enjoying filming them. I do miss our maths lessons. I do hope that when I'm asking questions to the screen, you're shouting back the right answers at me, or at least shouting something back at me. Makes me feel like I'm back in the classroom. Do log into this channel again to have a look for the day 3 answers. Thanks. See you later.